Introduction to lecture 27. Welcome back. In the last video we have seen how to solve initial value problem for a wave equation in the old domain, that is full real line. So, initial value when you are providing, so how to solve that problem. So, we have seen that. So, what we derived is the D'Alembert solution in the because we have used Fourier transform. So, basically the functions involved, the initial values and the solution itself, we assume that it is absolutely integrable function, and that means it goes to 0 at infinity. So, but in reality, but when you look at the wave equation, so when you model the wave equation, so wave equation need not be going to be 0 at the solution or the displacement at infinity, it need not go to 0, but infinity, there is no such infinity in reality. So, at infinity you can safely assume that there is no wave. Okay. Practically you can think of having no energy at infinity, because there is no such there is nothing like infinity. So, that is a notion, mathematical notion. So, if you assume that these initial functions and the solution function, if they are absolutely integrable, that means they are at infinity, they tend to 0. Then you can assume, you can apply the Fourier transform, and that is what we have done, and we derived the solution which is D'Alembert solution. But when you apply other methods, for example, if you directly can solve this wave equation, this initial value problem for the wave equation in the full real line, we do not assume this solution or the initial values that are going to 0 at infinity, but still you derive the same D'Alembert solution. Okay. So, in both the cases this is true. So, by Fourier transform you can solve this problem assuming that the waves at infinity, at both the infinities, minus infinity and plus infinity, they tend to 0. This wave energy will be tending to 0 at infinity. With that assumption, you can simply apply the, formally you can apply the or legitimately you can apply this Fourier transform and derive the D'Alembert solution. And even when they are not actually in reality, so this wave energy need not be going to 0 at infinity, still formally you can apply the Fourier transform and get the D'Alembert solution, because that is just extension of what we have done. Okay. We have solved the problem assuming that the energy at infinity going to be 0, but it need not be true. So, need not be 0 at infinity, still you have the same solution, that is D'Alembert solution. This is what we have done in the last video. And we also have seen how to solve a Laplace equation, which is actually steady state heat equation. We have solved the Laplace equation in the upper half plane. That means you can think of the domain, that upper half plane, as a plate, upper half plane as a semi-infinite, it's a kind of big half plane plate with boundary being y equal to 0, that is x axis, and which is at steady state, that is at -1 to 1 on the x axis. You keep the boundary data, that is keep the temperature constant temperature, you maintain constant temperature, say 1, between -1 to 1, and outside on the x axis you maintain a temperature 0. So, with that boundary solution, boundary condition for the Laplace equation, which is the steady state heat equation, what you are looking for is when hot plate, when your plate is upper half plane and which is heated, and which after some time, if it reaches the, when it reaches the steady state, and what happens is the heat is distributed all along this big infinite plate. So, the problem is to find the distribution of this heat, there is the temperature distribution of the plate by keeping the on the boundary, while keeping the boundary at certain temperatures. So, for example, here between -1 to 1 you kept the temperature 1, and outside on the x axis, that means at y equal to 0 and x belongs to minus infinity to -1 and 1 to infinity, you keep the 0 temperature. Then what is the temperature distribution of this plate in the upper half plane? That is what we have seen, but we find the solution being a kind of integral, solution being integral, but that is oscillatory type of integral. So, computationally is not good. So, this integral you cannot compute because of oscillatory terms in it. So, we will try to simplify in this video and get you a nice form of solution that is in a computable form. Okay. So, and then we will solve some other problems. This is the formal solution as an integral. This is kind of oscillatory kind of integral, because you are doing e power I xi x. To avoid this oscillatory kind of thing, we can derive another form of the solution just by applying the technique that evaluation of the integral we have derived. So, Parseval's identity kind of technique we use. So, what we use is kind of before I do this, we will try to use this technique. So, let me use this. So, you have this Fourier, you have this convolution product, which is if you take the Fourier transform of this on this. Okay. So, then this will become this, and what you get is f cap of xi times g cap of xi, right. So, what we have is 2 root 2 pi, root 2 pi is the what you have. Okay. So, if you apply the inverse transform both sides, what you get is this one, and you have this inverse transform for this inverse transform of this full thing. So, if I say f inverse of x now, this is the function of x now. Okay. This is what you have, and instead of f you start with f is a function of x, and you start with some function of xi whose inverse transform, Fourier inverse transform of f of xi, which is function of x. If I write like this, if is inverse cap, inversion let me write like f cap, f invert cap of x. That means it is actually originally it is a function of xi, for which if you apply inverse transform, what you end up is function of x. So, if you choose this, if f is f of x is equal to some function, if I replace f inversion, which is a function of x originally f of xi, on which you apply this, that is function of x. And then what happens if you write this same thing, what you end up is f inversion convolution with g, which is a function of x. Here if you apply the inversion, so you have the inversion here. So, f inverse, let me write here f inverse root 2 pi. So, that root 2 pi you can always write outside, and here instead of f you have f inversion. So, f inversion with f cap, that will be cancelled. What you end up is simply f right, f of x times here right. So, what you get is f cap of xi, and you have inversion. So, if you do the inversion, so you end up getting f xi. So, you have f of xi times g cap of xi, okay, which is function of x. This is the identity we use to simplify this. Okay, simplify that solution u of x y for x positive, x belongs to full R and y is positive. Okay. So, we will see how how we use this. What I start with is inverse transform of. So, here I use this inverse transform. So, first thing I use is this is the u of x y is 1 by pi times, rather if you write 1 by root 2 pi root 2 by pi, so that you have 1 by root 2 pi, that is actually root 2 goes pi, so 1 by pi, and this is minus infinity e power minus mod xi y times sin xi by xi e power I xi x d xi. So, that is exactly your u of x y. So, this is your f of xi. F of xi is e power minus mod xi y. Y is a constant. Okay. So, if you take this inverse transform of this, okay, that means here you want here. So, you end up, so this is actually equal to root 2 by pi inverse transform of root 2 pi times. So, you have a root so root 2 pi, one more root 2 pi, right. So, you have so root 2 pi f cap of xi times g cap of sorry wait so this is f cap of xi. So, this is f of xi and this is some g cap of xi, that is sin xi y. Okay. So, let me write this as e power minus mod xi y times sin xi by xi. Okay. So, that you have, if to make this Fourier transform I need 1 by 2 pi. So, that 1 by root 2 pi, so what you get is 1 by 2 pi, root 2 pi goes and then that is the 1 by 2 pi. Okay. So, you start with f of xi is this. So, if I apply this technique, this equality, what you end up is root 2 goes root 2. So, what you get is 1 by pi times root 2 pi, okay, 1 by pi times 1 by root 2 pi, this together, and this is in the place of this I use this one. So, that is minus infinity to infinity, there is a convolution product of the Fourier transform of this part. So, root 2 pi times e power minus mod xi y, for which you take the inverse transform, which is a function of x. Y is there anyway, y is a constant. So, eventually this is the inverse transform of. So, let me write instead of cap, inverse cap, you write f inverse of this, okay, f inverse of this if you do, which is a function of x, and then other one is g of. So, that is, so which is you have to see what is the inversion of this, inversion of if you write this inverse, f inverse of sin xi by xi, which is a function of x. So, x minus y, right. So, what is the convolution? Convolution is this is f of this is a function of this you call is y and you some z, okay, z is in the place of x and this is going to be x minus z dz. This is the convolution. Convolution variable is simply z variable I used, okay, z is a real number. So, I need to calculate f inversion of this and f inversion of this, that is all. Then I put it together here. So, that is the form you want to derive. So, you want to simplify your solution. So, to start with this f inverse of root 2 pi times e power minus mod xi y, y is a constant which is a function of x. If you look for what happens 1 by root 2 pi by definition minus infinity to infinity root 2 pi, that goes e power minus mod xi y, y is constant, e power I xi x dxi. So, this is exactly what you have. So, you have minus infinity. So, you split this into 0 to infinity like we have done earlier. You can write 0 to infinity. When it is 0 to infinity, so it depends on y is positive, y is anyway positive. Since y is positive, we know that is y is positive. So, xi is when xi is positive, you can write e power minus xi y, e power I xi x dxi plus minus infinity to 0. When xi is negative, so you have this is xi, y is positive, e power I xi x dxi. So, what you end up is this is xi. So, if you rewrite this is e power xi times minus xi times y minus I x d xi plus minus infinity to 0 e power xi times y plus I x d xi. Simply integrate this to get 1 by y minus I x e power minus xi y minus I x. For this you apply the limits, because xi is positive, y is positive, this is going to at infinity this is going to be 0, and this is also similarly you can do this y plus I x, and you have e power xi y plus I x. This is from minus infinity to 0. If you apply the limits, infinity contribution is 0, minus minus plus you end up getting y minus I x. Okay. This is at what I am putting xi equal to 0 to xi equal to infinity, and xi equal to 0 this is 1, and minus minus plus, so you have this one, and here at minus infinity this contribution is 0, so you have ending up getting y plus I x. So, together this is actually y square minus I square, that is plus x square, y square plus x square, and y plus I x, so you have 2y. Okay. So, this is what you have to replace here for this, and to see this one f inversion of sin xi by xi you do not have to calculate, we already have here. So, this is your u xi y is this u cap of xi 0. From this u cap of xi 0 is equal to root 2 by pi y equal to 0 if you put, that is going to be sin xi by xi. Sin xi by xi. So, what is u cap of xi 0? We know u cap of xi 0. U cap of xi 0 is this. That implies if you take both sides inverse transform, what you end up is you are getting u x at 0. U x at 0 is the inverse transform of root 2 by pi times inverse transform of sin xi by xi. So, this is what we use. So, root 2 by pi, if you bring it, root pi by 2 comes out here. So, pi inverse of that we will replace here. So, if you do that, so what you end up is u of x y is equal to, let me write 1 by pi root 2 pi, 1 by pi root 2 by pi, 1 by pi times 1 by root 2 pi. Instead of this integral minus infinity to infinity, instead of this you have 2 y by y square plus x square, that is for f inversion of root 2 pi, this one. Okay. And for this you can replace u at root pi by 2 times u at u of x minus y. So, if you do that, this is a function of z, so I replace, instead of x I replace z square, and here root pi by 2 times u at x, that is u at z x minus z, you have to replace x minus z. So, u at x minus z 0 dz, this is exactly what you have. So, this is actually equal to root pi goes. So, what you end up is then this 2 goes, this root pi goes. So, what you end up is minus infinity infinity, and you have minus 1 to 1 y by y square plus z square, and u of x minus z, what is u of x minus z? What is u of x 0 is this one. So, this is x minus z, u of x minus 0, u at x minus 0 is, you can use the initial data here, that is 1 if mod x minus z is less than 1, less than or equal to 1. So, that means z is the independent variable. So, z is between x minus 1 to, what exactly is this, x minus z is between 1 and minus 1, and you have z is minus z is between 1 minus x, right, minus x, 1 minus x, and if you do it place 1 plus x here, and you have a minus 1 plus x. So, z is that. So, z is between 1 plus x to minus, so minus 1, maybe this is not the way. So, you can say z minus x is also same. So, z you want 1 plus x, this side minus 1 plus x. So, this is easier. Okay. Mod x minus z is same as mod z minus x. So, if I use this, there is no confusion. So, you end up getting this one. So, z is between minus 1 plus x to minus 1 plus x, and its value is 1, which is dz. So, this is exactly your function of x y. This is the solution what you get for the problem. So, you can also work out if u of x y u of x 0, if this is as an initial condition, as a boundary condition, if you have as a function of x, you can simply replace f of x with there. Okay. Some simply function of x minus y. So, you can write x minus z here, so that it is integral minus infinity to infinity. So, finally, this is the form which is nice form, which is a computable form of solution. Okay. So, this is the solution for this semi infinite plate, upper semi infinite 2 dimensional plate, which is at steady state condition with the initial, with the boundary data is provided. For that boundary data, this is the solution, this is its solution everywhere else in the upper plane. So, let me do this. So far we have done wave equation and Laplace equation, that means hyperbolic equation and elliptic type of equation. So, let us do parabolic type, that is heat equation. We can also solve heat equation, boundary value problem for the heat equation, solution of heat equation. Heat equation, one dimensional heat equation. Let us say you consider a full rod, big rod from minus infinity to infinity. So, long rod, both sides infinity, such a big such a long rod, one dimensional, so that this lateral heat is not insulated laterally, that means only going temperature, heat flux is moving only in the one direction. So, that is one dimensional wave equation. So, along this is your x is from minus infinity to infinity. You have this, this is governed by the heat, the temperature in this rod is governed by for all times is governed by u of x t is the temperature, that is governed by dou u by dou t, which is equal to k kappa, sorry, that is the depending on the material constant, heat specific heat constant, that is depending on the material of this rod, k, and you have a one dimensional rod. So, you have only dou square u by dou x square, x is minus infinity infinity and t is positive. So, you do not have any boundary here. So, you have to provide only, except you have to provide only initial condition, that is u at x comma 0, and that is equal to that you can provide as some function of x. That means, initially this rod is at some temperature. What happens at all times, okay, at different times, how it diffuses in this under these conditions, how the heat diffuses in this rod. Initially, let us say if it is like this, x between minus infinity infinity, some function you can give, this is the given initial condition. and you also have a boundary data because the boundary is minus infinity infinity. If you want to apply again, so if you want to apply Fourier transform, you can expect at infinity, is natural that naturally you can expect at infinity there is no temperature at in the rod. Okay. So you can say that u x t goes to 0 as mod x goes to infinity. That is the boundary boundary condition. Boundary condition. So how do we solve this boundary value problem? Together it is called the initial boundary value problem. There is no not actually boundary, so you want to apply the Fourier transform, you need this, which is physically expected. So that is why we are saying this boundary condition. So this is basically initial value problem for the heat equation for an infinite rod. So the solution, we apply the Fourier transform. If you apply the Fourier transform, because domain of x is minus infinity infinity, you can apply the full Fourier transform. If you apply full Fourier transform, apply Fourier transform on x variable to get, what you see is if you apply on this, you get dou u cap of u of x t become u cap of xi t dou t, this is equal to kappa times I xi whole square u cap of xi t. If you apply twice two derivatives, you get I xi comes out square as square. So this is what you get, and xi is anyway full real line and t is positive. So this is what the equation becomes. What happens to the initial condition? Initial condition is u cap of xi 0 is f cap of xi. That is straightforward. Xi belongs to full real line, and you can here also u cap of xi comma t goes to 0. So boundary means if you apply the boundary, so really do not apply. So we do not use this one simply because of this we are able to apply this Fourier transform, because it has to go to 0 at both the ends infinity, then only this Fourier transform as an integral makes sense. Okay. So otherwise in general we do not need to provide this, we are writing this because that is physically expected, and also so that we can use the Fourier transform. Okay, this boundary condition. So this is what we want to solve. The equation now becomes u cap of xi t dou u by dou t, and this becomes minus minus plus this side. You have k kappa xi square u cap of xi t equal to 0 for t positive, and xi belongs to minus infinity infinity, and u cap of xi 0 is f cap of xi. This problem, this is a ODE in single variable ODE, so you can solve it. If you solve this first order ODE with respect to time derivative, so you can see that u cap of xi t, so this is your p, this is like a linear equation, dy by dx plus py equal to 0. So if you apply e power integral p dx, dx is the independent variable, so what we have is the t is independent variable here. Multiply this both sides, dy by dx plus py equal to 0. So this is actually equal to e power integral p dx times y, for which full derivative. So this is exactly same as this. So if you do apply that, what you end up is getting u cap of xi is equal to e power, so when you apply this e power integral k xi square, that is a constant, so you have instead of dx you have dt. So simply you have e power k xi square t, that is your integrating factor. Okay. So this is called integrating factor. So that is what it is. So when it comes the other opposite side, you have e power minus kappa xi square t times C, the constant. Okay. This is the general solution of this ordinary differential equation. So, if you apply this condition, u cap of xi 0 equal to f cap of xi, which is equal to, when you put t equal to 0, this is what you get, C. Okay. So, this becomes this and this becomes simply this. So, that means at t equal to 0. So, that means C you find. So, now your solution is f cap of xi e power minus kappa xi square t. So, that is all. So, you have xi belongs to full R and T positive. So, if you want to find how the temperature behave in this rod for all times, initially at temperature Fx, and you simply take this inverse transform, taking inverse transform, inverse Fourier transform, we get, what we get is u of x t is equal to 1 by root 2 pi integral minus infinity to infinity f cap of xi e power minus kappa xi square t e power I xi x d xi. This is exactly what you have. X belongs to full real line and t is positive. So, this is actually your solution. This is again like earlier, we can simplify further by looking at Parseval's identity. That is what we will see now. So, to see this integral, to simplify this integral, this is actually solution, but that is oscillatory type of things, which is not in a computable form. The solution is not in a computable form as an integral. So, what you do is we will try to, we have already seen that I think we have seen earlier otherwise let us work out e power minus a square x square. If you take this as a function, if you take the Fourier transform for this, what you get is 1 by root 2 pi. Fourier transform of this function is minus infinity infinity e power minus a square x square. So, into e power minus I xi x d xi, no dx. Okay. That is what you have. So, this is equal to, let me put it 1 by root 2 pi minus infinity infinity. So, what I do is I try to make it as a square here. So, e power minus I have a x, a square x square, a x plus something square. So, what exactly is that? A x. So, if you do that 2 times a x and times what you need to have is I xi by 2a. If you have, suppose you have, then I end up getting e power I xi x. That is exactly what I have. Okay. So, if I have to replace this something as I xi by 2a, then a square x square I have here, 2ab, that will be this. So, you also end up getting e power minus I square, what is minus plus xi square by 4a square. This is already you have here. So, you have to compensate with minus. So, that is exactly what you have to add here, minus xi square by 4a square dx. Okay. So, this is equal to e power minus xi square by 4a square times 1 by root 2 pi, and you have integral minus infinity to infinity. Like earlier, you simply, so we have used actually earlier. So, what you end up is e power minus a x plus I xi by 2a whole square dx. So, like earlier, you can construct this is your x axis, this is your x axis from minus infinity to infinity. You consider this rectangle. So, e power ax plus So, if you construct this, if you take this as a contour integration, the complex integration, if you consider this integral is same as this integral from this to this. Okay. So, that is same as saying if I choose Ax plus I xi by 2a as some t, a dx equal to dt, as this is a constant. So, you have e power minus xi square by 4a square 1 by root 2 pi. This is actually, if you do that, I have to change this to minus, I have to write I infinity minus at infinity as at x, at infinity minus infinity plus I xi by 2a to plus infinity plus I xi by 2a times e power minus t square, dx is dt by a. So, a comes out, which is a constant. So, this is what you have. Okay. But then if you use the contour integration like I have seen in the earlier videos, you end up seeing that this integral over this is same as this one. So, this will be, you can easily see that this is same as this by contour integration. Okay. So, this is actually equal to e power minus xi square by 4a square 1 by root 2 pi times a, and this value is root pi. Is from calculus. Okay. Make it a double integral from minus infinity infinity minus infinity infinity e power minus x square plus y square dx dy. Use the polar coordinates, you calculate, and then but this is same as I square. This is, if you call this as I, this is, you can split this because x and x y variable, y variables are independent. You can, they are separated. So, you have, this is like this one, e power minus y square dy. So, these are same integrals. So, you have I square here. So, this whole thing is I square is equal to, what you end up is pi by polar coordinates. If you substitute x square plus y square as r square. So, e power minus r square r dr d theta, and this is from 0 to infinity and 0 to 2 pi. If you do this, you end up getting this value as pi. That is what you have to see. So, by seeing that, I value will be root pi. So, that is how I calculated. So, I think I have explained earlier in the, I think I have already explained in the earlier video this idea. So, if you cancel this, you end up getting e power minus xi square by 4a square by root 2 a. Okay. So, the inverse transform of this is e power minus x minus a square. From this you can write inverse transform of, if you take both sides inverse transform, you end up getting 1 by root 2 times a e power minus xi square by 4a square. Take the inverse transform, f inverse transform, which is a function of x, is nothing but e power minus a square x square. This is exactly what you have. Now, what I do is I try to choose, I choose a as a square as 1 by 4 kappa t. If I do that, a will be 1 by 2 root kappa t. So, put it here in this, so that you have f inverse of 1 by root 2 times a times a will be is 1 over 2, 1 over 2 means you have 2 goes up, 1 by a is root 2. So, 2 times root kappa t times e power minus xi square by a square is 4 kappa t is equal to e power minus x square by 4 kappa t. This is what you have. Okay. So, you have what you have is root to root 2 goes, you can put it here. So, 2 under root. Okay. Root kappa times exponential of minus this is this. Okay. So, Fourier transform, if I bring this Fourier transform this side, if I apply Fourier transform both sides, this goes, you end up getting function of xi is this. Okay. So, this is what we use, this one. So, if you use, what happens to your u cap of xi? U cap of xi is this, u cap of xi t. What you have is u cap of xi t equal to f cap of xi times e power minus kappa xi square t. So, this is equal to f cap of xi. So, you try to use this one e power k a square xi square by, oh, so I think I made a mistake here. So, xi square by 4 a square, 4 a square is, oh, I made a mistake here. So, root, this is okay, this is root 2, 1 by a is 2, so that is root 2 k, this is okay, and this e power minus xi square by 1 by 4 times xi square by 4 times a square is 1 by 4 kappa t. So, 4 goes, kappa t goes up, xi square kappa t. So, this is exactly what we need, okay, and this is okay, this is fine. This so you end up writing this one with this. So, times, so e power kappa t, this I replace with this 1 by root 2 k t, this is anyway constant, t is constant, and this Fourier transform of this one x square by 4 kappa t, for which you take the Fourier transform. So, this by this is this, okay. So, if you use now both sides Fourier inversion, so this is equal to 1 by root 2 pi times 1 by root 2 kappa t. So, I multiplied this, so you have a root 2 pi f cap of xi times Fourier transform of minus x square by 4 kappa t, which is function of xi. Okay, this is exactly your u cap of xi t. So, you take the Fourier inversion on this u of x t left hand side, and this is going to be root 2 pi times 1 by root 2 k t. This Fourier inversion of this one, you have seen this f convolution of g of x equal to, if you take the Fourier transform of this, is equal to Fourier f transform of this with root 2 pi times g cap of xi. That is exactly what I have, f and g, this one root 2 pi you have. So, if you take the inverse transform for the whole thing, so you have this inverse transform of this is exactly this one. So, you try to write, so this into, this is the convolution you have to write for this, f is f of x or f of y times convolution e power minus, in the place of this you have x minus y whole square divided by 4 kappa t dy. That is the convolution. Okay. So, if you write this as 1 by 2 comes out root k pi t times integral minus infinity u of x t is f of, let me use a new variable, some, okay, you can use the y is not at all there, the dummy variable f of y e power minus x minus y whole square by 4 k t dy. This is for x belongs to minus infinity and t for all t positive. So, this is exactly the form of solution you are looking for, which is in a computable form. There is no oscillator integral. So, this solution you can easily compute for all x and for all times at every value of x. Okay. So, this is how you can solve heat equation, one dimensional heat equation with initial data. That means you have infinite rod with initially at some certain temperature. What happens after at later stage, at later times what happens, how the temperature distribution in the rod. So, that is what exactly you see as a solution. Okay. If you solve by, this is solved by Fourier transform. So, this is how we solve this boundary value problem, which is basically temperature distribution in an infinite rod, and initially at temperature initially at certain temperature, let us say f of x. Okay. We solved purely based on this Fourier transform, we solved it. We can also solve other boundary value problems depending on the domain. So, if your domain is only semi-infinite domains, for example 0 to infinity, x domain is or for example if you consider a Laplace equation in the quarter plane or in the upper half plane, or semi-infinite rod of temperature distribution in the semi-infinite rod, that means spatial domain is 0 to infinity. You can also apply your x domain is 0 to infinity, so that you can apply Fourier sine or Fourier cosine transform. So, we can also see such problems where we apply only we will see the application of Fourier sine and Fourier cosine transforms. We will see that in the next video. If time permits, we will move on to Laplace transform. So, we will define what is Laplace transform. We will give you the motivation in the next video. Thank you very much.